Hey, hello. Let's start today's class. In this lecture, we will explore the p-n junction corresponding to chapter 7. When p-type semiconductor is joined with an n-type semiconductor, a p-n junction is formed. We will learn about the physical phenomena that occur when such a p-n junction is created and how to interpret them. First and foremost, in this class, we will attempt to qualitatively interpret the p-n junction through energy bands diagram. That is, we will try to draw energy bands as much as possible without deriving equations and practice understanding the concept based on these energy bands. So before delving into the details of p-n junction, let's briefly overview the fabrication process. Since this class is not focused on fabrication, we won't go into the intricate details. To create a p-n junction, start by preparing a p-type wafer. Then, ionizing donor ions that can create an n-type region and shoot them in the form of an ion beam onto the wafer. So this process allow the donor ions to penetrate to a certain depth, forming the n-type region. So this method is known as ion implantation. In practice, masking materials such as PR, photoresist, or SiO2, SiO2 are often used to selectively form the n-type region in desired areas and taking into account the diffusion of dopants. The resulting p-n junction created through this process typically forms a junction in the vertical directions, right? However, for the interpretation, it is common to express the n-type and p-type semiconductors as adjacent in horizontal configuration. So this p-n junction exhibits rectifying IV characteristics acting as a rectifier or diode. When a voltage is applied, current flow easily in one voltage polarity, but it doesn't flow as well in the opposite polarity. This characteristic makes p-n junctions fundamental to the structure of LEDs, solar cells, and all forms of transistors. Therefore, understanding p-n junction is crucial for theoretical learning of semiconductor devices. Here, one additional assumption needs to be made. So when creating p-n junction, we injected donor ions into a p-type wafer doped with the concentration of Na to convert it into a n-type, right? In other words, in this region, originally there were acceptor ions, right? Originally, there were acceptor ions present, and with the injection of donor ions, the situation that ND donor ions have been added. Therefore, the electron concentration in this region, N type in this region, would be ND minus NA, right? Because originally it was a p-type wafer, but because of ion implantation of donor ions, the concentration of ND are doping in this region. So the final concentration will be ND minus NA. In actual fabrication processes, situations may arise where acceptor and donor ions are mixed. However, for the theoretical interpretation of p-n junctions, considering such complexities would make the analysis too intricate and confusing. Therefore, when referring to doping concentration in the future, it will denote the doping concentration of pure donor ions in that region. For instance, if there are donor ions in the p-type region, we will denote the concentration by subtracting the donor concentration from the original acceptor concentrations and call it Na. And similarly, by subtracting the acceptor concentrations from the original donor concentration, we will denote the net donor doping concentration as ND. During the class, when we mention Na or ND, please remember that it directly signifies the concentration of holes and electrons, excluding complications arising from this fabrication process. Now, let's interpret the p-n junction in detail. Let's assume that N-type and p-type semiconductors, it's doped with a concentration of 10 to the 16th power, form a junction. When interpreting semiconductor devices, the first step is to draw the energy band diagram. As mentioned before, the EC level represents the potential energy of electrons in the conduction band, and the EV level represents the potential energy of holes in the valence band. Therefore, the energy band diagram represents the positions of EC and EV level based on electrons and holes. Once the energy band diagram is drawn, it becomes easier to predict how electrons will behave. To draw an energy band diagram using the given doping concentration information, here is what we can do. So we have learned the following equations where the doping concentration where the doping concentration is equivalent to the concentration of major carriers in each type, allowing us to determine EC minus EF and EF minus EV. So if the PN junction is in a thermal equilibrium state, there is only one Fermi level, and it must be drawn horizontally. Therefore, a single and horizontal Fermi level is expressed. Since the left side is an N-type semiconductor and right side is a P-type semiconductor, you can express them using the Fermi level, using this Fermi level, and the difference in EC and EV levels, right? While the exact connection in the middle may not be precise, drawing a lovely smooth. So like this smooth connection represent the energy band diagram for the PN junction. So it is crucial to note that this energy band diagram of the PN junction, this energy diagram represent the energy band diagram of PN junction under the thermal equilibrium, right? It is under thermal equilibrium state. The next step involves interpreting the energy band diagram to extract detailed information. In the current scenario, where the energy band diagram is inclined to the bottom left, the electron's position energy on the left is lower than that on the right. Consequently, electrons will move towards the lower energy sides, akin to rolling down a slope. Conversely, holes having lower energy toward the top will move toward the right in the energy band diagram. In essence, if you can draw the energy band diagram, you can disconcern the direction in which electrons and holes will move. So from our learning in chapter 3, we know that we can obtain valuable information through this process. The most noticeable point is that the middle region must be curved. In the region where the energy bands looking like in this, there exists an electric field. So here will be an electric field, right? And the direction of the electric field aligns with the sign of the slope. So given the current positive slope, we can anticipate that the electric field will be generated from left to right based on these energy bands. So in summary, interpreting the energy band diagram provide insights into the movement direction of electrons and holes. And in this case, it suggests the presence and direction of an electric field in this curved region. So by examining the energy band diagram, we have learned that an electric field is formed at the junction when a p-n junction is created. Now let's consider why this electric field occurs. On the left, we have an n-type semiconductor where electrons, the major carriers, are abundant due to donor doping. In thermal equilibrium, this n-type semiconductor is neutral. Similarly, the p-type on the right, containing holes and acceptor ions, maintains neutrality. However, what happens when we join these two regions? What happens? So on the left, there is an excess of electrons, while on the right, there is a scarcity of electrons. So as a result, these electrons will diffuse toward the right? They are going to diffuse in this way. Oh, however, since the right side is a p-type semiconductor with a high concentration of holes, so as electrons diffuse over, they will recombine with holes, and they are disappear. So they are disappear because of recombination. Therefore, electrons that diffuse across will instantly recombine with holes in the p-type region and vanish. The same phenomena occurs in the n-type semiconductor. Holes in the p-type semiconductor diffuse from regions of high concentration to low concentration, and these diffuse holes immediately recombine with electrons and recombine with these electrons and disappearing. Therefore, carrier diffusion occurs, and the diffused carriers recombine on both sides, leading to their disappearance. After this recombination, a vacancies are created where carriers have left. In other words, when electrons move across and recombine, the region is left with the immobile atomic nucleus of donor ions, which carry which carry a positive fixed charge. Similarly, in the region where holes have existed, I mean, the where the holes are exited, only the fixed charge from acceptor ions carrying a negative charge remain in this region. In summary, electrons from the n-type region diffuse into the p-type and recombine, disappearing. Similarly, holes from the p-type region diffuse into the n-type and recombine, vanishing. Consequently, in this junction region, only the plus fixed charge due to donors and the minus fixed charge due to acceptors remain, creating an electric field from plus to minus. This internal electric field is represented by the bending of the energy bands in the energy bands diagram. When a p-n junction is formed in this way, an internal electric field is established due to the fixed charge. So this is because of fixed charge, right? This generated electric field prevent the diffusion of electrons trying to move from the left to the right. Since the electric field points from left to right, the electron's diffusion direction is to the right. But the electric field induced throughput. Electric field induced throughput is in the left direction. As a result, these two effects cancel out, preventing electrons from diffusing further. Alternatively, interpreting in terms of energy levels, during the summer equilibrium, the fact that electrons are diffusing to the right implies that they are transitioning to higher energy levels. It can be viewed as the creation of an energy barrier for this electron, right? So to overcome this energy barrier, additional energy must be applied, right? With this additional energy, this electron can overcome this energy barrier and they can diffuse into this region. But the problem is, however, during the summer equilibrium, there is no additional, right? There is no additional energy in summer equilibrium. So it caused the electrons to be unable to overcome this energy barrier and cease further movement. In essence, the force attempting diffusion countered by the built-in electric field restrict the electron's motion, or one can think it as the creation of an energy barrier for the electrons. And next, let's consider the charge density low. In thermal equilibrium, a typical semiconductor is neutral, maintaining neutrality in both N-type and P-type regions. Consequently, the charge density graph for these two regions will have a value of 0 because these regions are neutral region, right? But in the junction region, both plus fixed charge and minus fixed charge remain. Therefore, in the N-type region, the area with remaining plus fixed charge, the charge density is formed by multiplying the doping concentration by the charge of donor ions. Similarly, in the P-type region, due to an acceptor ions, a charge density of minus E and A will be present. In summary, in the p-n junction, the regions on either side are neutral, but in the junction region, a non-neutral states exist and the charge density can be inferred accordingly to this graph. Similarly, let's consider the concentration of mobile carriers. In the N-type region, the electron concentration is determined by the amount of donor doping, right? So it is determined by donor doping. Likewise, in the P-type region, the whole concentration is equal to the concentration of acceptor ions, right? So they are equal to acceptor ions. But this region, this region where carriers are absent is known as the depletion region, or space charge region. So in reality, the carrier concentrations change through some distribution, assuming a Chap boundary. So it may have these kind of things, right? Actually, they have this kind of distribution, assuming a Chap bound, but assuming a Chap boundary help just simplify the derivation of equations. So just assuming like this is known as the depletion approximations. So for a p-n junction in thermal equilibrium, carriers undergo diffusion and recombination in the junction, leading to the formation of a depletion region where mobile carriers are absent, but there are still fixed charge. So within this depletion region, only fixed donor and acceptor ions remain and creating a built-in electric field. This built-in electric field counteracts diffusion, and in thermal equilibrium, carriers come to last without further movement. Let's proceed with the mathematical analysis. In a p-n junction, the Fermi levels of p-type and n-type semiconductor need to align horizontally, right? They need to align horizontally to create bending. The difference in Fermi levels as indicated by the arrows eventually becomes the size of the bending of the p-n junction, right? So it becomes the bending in the p-n junctions. These sides can be more easily calculated using the intrinsic Fermi level. If we have information about the intrinsic carrier density, Ni, and the carrier concentration P0 and N0, we can determine the difference between the Fermi level and intrinsic Fermi level EFI. Then we can calculate the total bending in the entire p-n junction by summing up these differences, right? So the energy band diagram for this p-n junction is as follows. So by adding the bending on the p-type side, right? And the bending on the n-type side, we obtain the total bending. We can get, when we adding this one and this one, we can get total bending, right? We can obtain the total bending of the energy bands. And this bending size is referred to built-in potential. Why is it called the built-in potential? In thermal equilibrium, when creating a p-n junction, internal difference in potential arise. Hence, the term built-in potential denoted as VBI. The reason for having E in front of VBI is that VBI is defined in volt. Since the energy level difference is typically calculated in electron volts, multiplying by E ensures unit consistency when defining VBI in volts. Okay, the difference between the Fermi level on the p-type side and the intrinsic Fermi level can be expressed as follows. At this point, the whole concentration is equal. The whole concentration is equal to the concentration of injected acceptors. Similarly, by substituting the electron concentration on the n-type With the quantity of injected donors, we can determine the total banding, which give us the size of the built-in potential. It is important to note that this equation is applicable only to non-degenerate semiconductors. As previously learned, there is a limitation to the maximum dopant concentration achievable in semiconductors. Beyond this limitation, doping cannot ionize the dopant. Highly doped semiconductors with concentrations greater than 10 to the 18th power are termed as the degenerate semiconductors, right? Actually, the current formula is derived from multiplying the density of states and the Fermi-Dirac function throughout the conduction band, followed by integration, right? For this calculation, the Boltzmann approximation was necessary during integration. That is, these equations cannot be used when the Boltzmann approximation is not valid, which implies it is not applicable for degenerate semiconductors. So when is the Boltzmann approximation valid? The Boltzmann approximation is valid when interpreting low doping non-degenerate. So it is only valid for non-degenerate semiconductors. Therefore, this formula is not valid when interpreting highly doped semiconductors with concentration exceeding 10 to the 18th power. Always keep these points in mind. Essentially, when interpreting a p-n junction with a very high dopant concentration, using this formula results in correct values. Okay, for non-degenerate semiconductors, the built-in potential can be calculated as follows. So, as you may notice during further derivations, the term kT over E frequently appears. Its unit is volt, and it is commonly referred to thermal voltage. So when looking at the derived expression for VBI, you will observe that since the remaining terms are constant, an increase in dopant concentration results in an increase in the difference between the Fermi levels of the two semiconductors, ultimately leading to a larger built-in potential. Finally, let's examine the p-n junction referred to as one-sided junctions and conclude the class. A one-sided junction implies a p-n junction where one of the p-type or n-type semiconductor is highly doped to the extent of being degenerate, resulting in a significant difference in doping concentration between the two semiconductors. For instance, if the p-type is doped to the 10 to the 19th power and the n-type is doped to 10 to the 15th power, creating a substantial difference in doping concentration, then these PN junction would be termed the one-sided junctions. So, what difference arises in a one-sided junction? In this case, to distinguish it from a regular PN junction, it is called the P plus N junction. The addition of a plus sign indicates that the doping concentration is very high. If you have created the P plus N junction, the p-type semiconductor being a degenerate semiconductor would mean that Fermi level is almost at the valence band level. So in this scenario, since the Boltzmann approximation cannot be applied, the previous formula cannot be used. So how can we determine the banding on the p-type side? In this case, assuming the Fermi level is nearly attached to the EV level, we assume that the difference between the intrinsic Fermi level and the Fermi level is approximately half of the band gap. Therefore, the banding on the p-type side becomes Eg over 2. So you can use the same banding on the n-type side. So similarly, for an N plus P junction where the n-type doping is highly degenerate, assume that the difference between the Fermi level and the intrinsic Fermi level is half the band gap. The rest of the calculation remains the same. So in summary, in case where semiconductors are highly degenerate, such as in one-sided junctions, you cannot apply the Boltzmann approximation, and you need to derive equations appropriately for its situation. Okay, so that's it for today's class, and thank you for the listening.